Good afternoon, everybody. Welcome again to another RUS webinar. My name is Miguel Castro, and today I will be guiding you through this quite interesting topic, which is crop mapping with Sentinel-2 data. So before starting, let me go very quickly through some organization details. First of all, what you can expect from this webinar. So during the next hour, more or less, you will learn two main things. First, how to do crop mapping analysis with Sentinel-2 data. And second, what is the RUS service and how it can help you when working with Sentinel data. So for this exercise, we will combine both RUS and the Sentinel data, and we will download, process, analyze, and visualize the free data acquired by the Sentinel satellites. If it's the first time you are here with us with RUS, I will show you where you can find all the past webinars, the videos, and most importantly, how you can repeat the exercise by your own. It's very easy. So that's all for the very brief introduction, and now let's get started and let's have a look to the outline for this webinar. So we will have a look first of all to the study area and understand the characteristics of the location we are using today. We will then cover very briefly the remote sensing background and understand how satellites can help in agriculture and in crop mapping. We will then describe the RUS service, and we will learn what are the challenges nowadays when working with remote sensing and why RUS is a great alternative to solve all those problems. And then we will use this RUS service to perform our exercise. So at the very end, we will have some time for Q&A. It will be more or less 20 to 30 minutes. But since we are quite a lot of people here together for this webinar, I will ask you please to send your questions as soon as you have them. So I'm here with a couple of colleagues and they are ready to answer your questions. So don't wait for the Q&A session. Send it to us through the question option that you have in this GoToWebinar tool, and we will reply to you right after. So as you can see, the duration of the webinar is going to be 1 hour 30 minutes, more or less. Let's get started. So today's exercise is going to be in the south of Spain, in a region called Andalusia, and more in detail in the south of its capital, which is Seville. So this area is known as the Guadalquivir Marshes and represents one of the last territories occupied by man in this Spanish region. Settlements were not definitive until 1940s, when the expansion of agriculture, especially rice, led to a complete transformation of the area. Nowadays, 35,000 hectares are used to grow rice, with an average production of 8,500 to 10,000 kilograms per hectare. So it's pretty intensive here. Other crops such as wheat, cotton, sugar beet, or sunflower can be found as well. So let's have a look very quickly to some historical images to see the creation and evolution of this agricultural area. So in this first image from 1945, we can see already the presence of agricultural fields in some areas, but also water bodies are still present. So we can see here some water bodies in the south of this area in this image. The next one from 1956 shows already clear agricultural patterns. And from this moment, the images from 1977, 2008, and later 2017 with Sentinel show the consolidation of the agricultural activities. So the blue line, just for reference, so you can compare. So knowing that, let's now move and check the remote sensing background behind the use of satellites for crop mapping. Reliable information on crops is required to improve agricultural management, reduce its environmental impact, and face food security challenges. For that, different methods can be used to gather this information, but satellite Earth observation techniques offer a suitable approach based on the coverage and type of data that are provided. The imagery data from the Sentinel satellites enable a new approach for agricultural monitoring, and the combination of the temporal, spatial, and spectral resolution together with relevant analysis can lead to improvements of the decision-making process. So for today's exercise, we will be using Sentinel-2 data. And more in detail, we will be using the multispectral data provided by this Sentinel-2A satellite. And in case it's the first time you heard about them, the Sentinel satellites are included in the space component of the Copernicus program of the European Union and the European Space Agency. And once completed, this program will be formed by 6 constellations of 2 satellites each, with a range of technologies from SAR to multispectral imaging. And last but not least, in case you don't know, the data are completely free to any registered user. So there is no charge for those images. So as you can see in this slide, just want to highlight 2 main characteristics of this satellite, which is the revisit time, which is 5 days at the equator, and the different spatial resolutions that we can find from 10 meters to 60 meters. So combining those characteristics with this great revisit time, we can improve and enable new applications with satellite remote sensing, such as monitoring activities for agriculture, etc. So, knowing that about the data we are going to use for this exercise, let's now have a look to the RUS service and understand what RUS is and what it's here offering to the Sentinel community. So first of all, RUS stands for Research and User Support for Sentinel Core Product. It is an initiative founded by the European Commission and managed by the European Space Agency with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. So what does that mean in other words? Well, with the large amount of data produced by the Sentinel satellites, the challenge is no longer data availability, but rather storage and processing capacity. So RUS offers virtual machines so that you have the appropriate computing environment to handle the data. But that's not all from RUS. In addition to that, RUS also provides a specialized user help desk to support your remote sensing activities with Sentinel data. So in case you are working, for example, as today in an area doing crop mapping and you are not sure about how to use the data, or you are not sure about how to solve specific problems, you can contact our remote sensing experts and they will come back to you with help and support for your projects. But that's not all from RUS, because besides that, we also have a specific training plan, specific training activities such as this webinar, but we also have face-to-face events where we train users on different applications. So you can find all the information about the RUS project and the RUS service in 2 main websites. Here we have the rus-copernicus.eu and the rus-training.eu. In the first one, you can find all the information about the project. The second one contains mainly all the information about our training activities. So let's go very quickly to those websites and have a look. So if we go to the RUS training, we can see here the homepage, and something that I wanted to highlight is this training tab here. If we click, we can access the past trainings. And this is very relevant because in case you have missed one of our webinars in the past, such as, for example, the one that took place in December for burn area mapping, well, you can come here, click on the webinar, and you will be able to see the video, and you will have also a Q&A session document where we summarize all the discussion that usually takes place during the Q&A session of the webinars, and of course some information about how to repeat the exercise. But don't worry, I will tell you in a few minutes how to do this exactly. Something also to mention is that we have recently launched our e-learning material. So here you can find courses and videos in an interactive way so that you can learn more about Sentinel, about radar, SAR, optical data, etc. So this is our RUS training portal. And if we go now to the other one, which is rus-copernicus.eu, we see here all the information concerning the project. So from here, I just want to highlight 2 things. If we go to the RUS offer and more in detail to the computing environment, we can see more in detail the virtual machines that RUS offers. So as I said, we are offering cloud computing power so that you can work with the data. And here you can see the specifications of those virtual machines. For example, the list of softwares that it's already available. This software is already installed and ready to use, so there is no need for any installation process. So for example, we see Snap, we can see also Python, R, and many other softwares. Remember that in the RUS virtual machines you have full administration rights, so you are able to install any software you want, either open source or proprietary software. But remember that in that case you need the license by yourself. So those are the softwares that we provide, and about the specifications of the machines, depending on your project and depending on your needs, you will have a different virtual machine with a different storage capacity and a different processing capacity. So here you can see all the details, and just to mention that in case you have a very large project that requires a lot of resources, there is an option to do clusters in the virtual machines and have more capacity. So knowing that, let's have a look now to the process of registering for RUS and applying for those virtual machines. The exercise of today will be done in one of those virtual machines, so I just want to show it to you so that you can know that and maybe use it in your own projects. Remember, I think I didn't mention that, but the virtual machines are free, so there is no cost for this. So if we go to the upper right corner to the login registration tab, we can first of all register for RUS. So we need to create a Copernicus single sign-on registration. So you just need to fill in all the information and confirm your account. So once you click the register button, you will receive a confirmation email and your account will be activated. And once you are done with that, you are able to log in RUS. So the process will be the same. We go to the login tab, and now we press on login. So I have here my account already, so I will log in. And now the relevant thing to mention is that there is a new tab that appears here. It's called your RUS service. And here you have three main options: your profile, where you can change the details of your account, but the most important one is your dashboard. So let's have a look. So here in your dashboard, you are able to interact with RUS and apply and access your virtual machines. So as you can see, I have already two virtual machines that are called RUS Training 1 and 2, and this is because I have already applied for those VMs. But if you are a new user, you will not have this, because the first thing you have to do is to apply for the virtual machine. And how to do that? It's very easy. We just need to go to the dashboard and click on Request a New User Service. So let's have a look to the process. So we have here a questionnaire where we have to fill in some details about our project. As I said before, depending on your project, you will end up with a different virtual machine with more or less processing and storage capacity. So it's here when you can specify your needs, where you can tell us the type of analysis you are going to do, the type of data you want, and in that way we can really understand your needs, and we can give you the cloud environment that really is beneficial for you. So let's go through this registration process very quickly. First thing to say, for example, is the years of experience. Also, if you have already worked with Sentinel data, if you have already handled Copernicus data. And here, and this is very important, you can insert the training code. So later on, once we finish this webinar, I will provide a training code for this exercise. And if you wish to repeat the exercise, you just need to register in RUS, go through this application procedure for the virtual machine, and here you will have to specify the training code. And that's very helpful for us, because in that way we know that you want specifically to repeat this exercise. So we will give you the virtual machine with the data and the software and everything ready so that you can focus on the analysis and don't waste time. So let's continue with our application for the virtual machine. We provide this information. The next thing is to specify more details about our project. So for example, what kind of activities are foreseen? For example, algorithm development or very basic data exploration, etc. Then there's another feature that is very interesting in RUS, and is that you can ask for us to download the data. So in case you are working with a large data set, for example, of a complete year over a study area, or in case you have a lot of study areas because you are running different projects, you can send us the request and we will download all the Sentinel data that you need. So you will just have to specify, of course, the sensing period, the type of product you want, and with those details, we will put all the information in the virtual machine, and once you access it, it will be there, ready to use. You will have the data, you will have the software and the computing power, and you will be able to focus on your research, only on your research. Anyways, today I'm going to do the downloading process myself, and here we can specify some extra details, okay? And then of course, let's put a name to our project. So today is going to be crop mapping. And then we click next, and the final thing to specify is the data. So what type of data are you going to use? So let's take the example of today. We are using Sentinel-2 data, and we are using level 2A. You can also combine other satellites if you want, but today it's only Sentinel-2 for us. The next thing is to define our study area. So in our case, we zoom in Spain, and we go to the south, next to Seville, and we can define here in the Guadalquivir Marshes our study area. You can also specify the lat-long coordinates, or even upload shapefile if you have it. Then another question, are you going to do a multi-temporal analysis, or are you just looking to a single image? So for example, in this exercise of today, we are only using one image, but in case you are doing a multi-temporal analysis, you can here specify the time. So I'll leave it as no, and here some extra information about the data if you want to give it to us. Remember that the more information we have about your project, the better we can understand what you are doing, and the better it will be so for the virtual machine and the environment you will be provided with. So that is all for the application procedure. The only thing now is just to review the application, check that all the details are correct. Of course, have a look at the terms and conditions of the service. Here you will find all the information about how RUS is organized. And if you agree with that, just click on the option and submit the request. So what will happen after that? The submission will be sent to our team, and within a couple of days, they will come back to you with the activation of your virtual machine. So don't worry if you don't receive an answer right after your submission. This is, let's say, a customized process where we check your project and we give you the best answer. So it takes a few days, I would say 2 to 3 or 3 to 5 more or less. So that's how it works. So knowing that, I'm not going to submit the request because I already have 2 virtual machines, so I will not send this one. So I will go directly to the dashboard where we can find what happens once it is activated. So let's go back to the dashboard. And once the RUS team comes back to you with the approval of your virtual machine, you will see this screen here with this table. So the project name that we have introduced before, etc. So what is relevant here to know? Well, mainly 2 things. The first one is the access my virtual machine option. So it's here where you can access the virtual machine and go into your cloud environment and do all the processing. In case, for example, you want to close the service because you are done with your analysis, you can also use this option. But something also very important is the get support. So, as I said, here in RUS we are providing also dedicated Earth observation help desk. In case you have doubts, in case you have questions about Sentinel data, you don't know how to apply a methodology for your specific application, etc. So it's through this get support button that you can click here and write us, you send us your question, and it will be derived to the appropriate people and come back to you later. Knowing that, we are ready to access the virtual machines and start our exercise. So let's go. We click here in access my virtual machine, and this is the environment you will find. So it didn't ask for the credentials because I was already logged in, but remember, once your virtual machine is confirmed, you will receive the link to the virtual machine, so it will be activated on the dashboard, and you will also have your username and password. So you will just have to put that and you will access the cloud environment. So here we are in this cloud environment. It's Linux based, so if you are a Linux user, you will recognize this. As you can see, we have some software that I have here in the desktop that it's already installed. As a regular computer, we have the internet browser where we can do a regular internet actions. We also have our file manager to store everything. So remember, we are working in a cloud environment, so all the data will be stored and will be processed in the cloud environment. We are not using the resources of our own laptops, and this is the advantage, because processing Sentinel data, it can be at some point quite a large task for our computers. So something important to know also with the virtual machine is that it's very easy to interact with your computer. So let's imagine you have downloaded 10 images of Sentinel-2 and you have done a crop mapping analysis, and you end up having the result we will end up having today. So this result, you might want to download it to your computer, maybe to print it, maybe to send it to some colleagues or whatever. So it's very easy. We just need to activate the appropriate menu. And this is done by pressing the keys Ctrl-Alt-Shift. By doing so, we activate this menu here. And now we can go to the device section, go to the path where we have our classification file or whatever data we want to download. And for example, I'm going to download this new classifier text file. To download it, it's very easy. We just need to double click and then a regular internet download process will start and you will have this file in your downloads. In case you want to upload something to the virtual machine, is exactly the same. We go first of all to the path where we want to save the data, and instead of double clicking on the file, we press upload file. So here the pop-up window appears and we can, for example, import this PDF. You can also import save files, raster images, or whatever you want. So this is the virtual machine we are going to be using, and now we are ready to start. So in this exercise, for this crop mapping analysis, we will perform a supervised classification using the random forest algorithm. So if it's the first time you heard about this algorithm, don't worry. I will explain it later how it works, at least in a basic way. And the analysis will be done using the ESA SNAP software. So let's get started, and for that, let's open our internet browser and download the Sentinel image we are going to use. So we go to the Copernicus Open Access Hub and we click on the Open Hub. So to download Sentinel data, you need a Copernicus account. So it's very easy. You just need to go here in the sign up in case you don't have one already, and just fill in the information. The activation is very fast. You will receive a confirmation email and you will be ready to download the free data from the Sentinel satellites. So I have already an account, so let me log in. Okay. So how to download Sentinel data? First of all, we select the pan option so that we can navigate on the map, and we zoom in. Well, we zoom in the south of Spain, next to Seville. So here is Seville, and we are focusing in the south, which is the marshes of the Guadalquivir River. This here is the Guadalquivir River. So here we are in our study area. Next thing to do is to define this study area, and for that we can either use the box or the polygon option. So I'm going to use the box option, but you can have your own preference. So this is going to be more or less my study area. The next thing is to specify the parameters of the image we want to download from the satellite. And for that we activate this side menu here and we specify the sensing period. So the image we want to use for our analysis is from 2017 June the 1st So it will be one image from that day. So we will again take the same reference for the ending of the sensing period. Okay, so then we do not want Sentinel-1 data. We are not doing a SAR exercise today, so we go down and we select Sentinel-2, and we will select a specific product type, which is the level 2A. So level 2A products over Europe are released by ESA since last year. So we can already work with bottom of the atmosphere values. So this is all the parameters we need, and now we just need to search for our images. So we click on this icon here, and here we have all the images that fulfill our query. So as you can see, we have 4 images in total, but the one we are interested on is the last one here on the list, which ends with 225. So we can see a couple of parameters about the image, for example, the mission, the instrument, the sensing date. But if you want to have more details about the image, you can click here in this icon, and there will be a menu where you can see all the information. So for example, more details about the size of the product, more details about the metadata of the image, etc. And once you are, for example, also a quick look of the image, which is sometimes very nice if you are checking for clouds and you don't want cloud presence. So we have here the image. It looks very nice, no clouds, so that's great for us. So if you are okay with the image and you are sure this is the one you want to download, you just need to press on this arrow icon, and the download process will start. So we save the image on our virtual machine, and the download process will start. So remember, we are storing everything on the virtual machine, not on our computer. I want to emphasize that because if we are doing a lot of processing with a lot of images, it's there where the virtual machine gets very useful. So I have already the image downloaded on the virtual machine. The process doesn't take that much, but I've done it before to save time. So we are ready now to have a look to the image and do the analysis. And for that, let's open, as I said, the ESA SNAP software. I have here the icon on the desktop. So let's open the software. Okay. So there it goes. So in case it's the first time you are seeing this software, might be, let me give you a very brief introduction. It's very easy to use. We have the product explorer area, where we will have all the files that we will be working with listed. You will see that later. We have here in the lower left corner some quick menus, such as quick looks of the image, color manipulation, etc. Again, you will see that later, how it's used. We have here this big gray area where the images will be displayed. And of course, we have all the tools that are needed to process the satellite imagery here in this bar, and also by menus. For example, the raster tools, the tools for optical data, also the tools for SAR data, etc. So it's a very complete package. So let's open our image and let's have a look. How to do that? Well, we have mainly 2 options. We can press here the open product icon, or we can go to File, Open Product, and then we navigate to the path where we have our image and we can open it. So in SNAP 5, when you download a Sentinel-2 image, it comes as a zip folder. So the first thing you have to do is to unzip the folder. And once it's unzipped, you have here the safe format that is used for the Sentinel-2 images, the safe structure, let's say, and we are looking for this specific XML file. This one will be the one that will open the image in SNAP. So we select it and we press open. And now SNAP is reading the file, and here we have the product. So this is our Sentinel-2 image. We see here the name with some key information such as the date, the tile, etc. We can expand the product to have a look to some folders such as the metadata folder containing all the information about the image. We also have the bands folder, which is the folder where we have all the image by itself. So we have band 1, band 2, etc. And now what we are going to do is to open a true color RGB composition. So for that, we right-click on the image and we select Open RGB Image Window. So we can so by default, Snap puts the true color combination for the red, green, blue channels, but you can also use other combinations or create your own ones. But okay, I'm going to use the true color today. So we click on OK, and there we go. This is our image. So first thing to explain, very easy, how to move around. We have here this pan option, this hand, we select it, and in that way we can move around. We can also use the zoom tool to zoom into our study area. So let's do it. And for example, a little bit more. Okay, so this is going to be the area we want to classify. As you can see, we have some fields over here. We will see what's that later. We have the river in the middle, and we have this area with different crops. So you can see a very large variety of crops that can be found here. So the first step in our processing is going to be resampling. So as I mentioned at the beginning when I was introducing Sentinel-2, Sentinel-2 has 13 spectral bands, but not all of them have the same pixel size, the same spatial resolution. So one of the main steps that are required most of the times, I would say, when working with Sentinel-2 data is to do a resampling. That is, we want to put all the pixels to have a common pixel size. So all of them having 10 meters, 20 meters, 60 meters, or any other, let's say, resolution that we want. So for that, we go to raster, and we go to geometric operations, resampling. And here we have the common, or the common interface that Snap uses for the tools. It's very easy, and especially easy to get used if it's the first time you are working with Snap. So we have here the input-output tab. Here we specify, first of all, which is the input for this specific operation we are going to do. So in our case, it's the product number 1. Check this index here in the image, number 1. We then define the output name. So by default, Snap adds a keyword of the tool we are using. And this is very convenient, I would say, because in that way you can keep track of your chain. And it's very easy to remember what you have done in case you are combining a lot of steps. So this is the name for the product, and now you can select if you want to save it or not. If you don't save it, it will be saved virtually in the memory of the program, so to say. But if not, you can also save it in your virtual machine. So I'm going to select this option, and just make sure that you are selecting the appropriate path to save the product. So, okay, and now let's have a look to the parameters of the resampling tool we are using. So in Snap, you can resample the images in 3 ways. You can use a reference band, you can use a target width and height, or you can specify the pixel size that you want. So in my case, I'm going to use a reference band because I think it's easier. So I would select band 2 as reference. I want all the bands to have the same pixel size as band 2. This is the meaning of this tool. And then we leave the remaining parameters as default, and we press run. So again, for timing issues, I'm not going to run the process, so I will directly open the result of this operation. But in case you are doing the exercise by your own, just press run and the process will start. So I will close this now and open my pre-processed image, which is here. Okay. Okay, so once the tool is finished, the new product will appear here in the Product Explorer. As you can see now, it has index 2, and it has this extra name added at the end. So of course, this is a resampled image, so if we open a true color, it will look exactly the same, so I will not go through that. And now let's go to the next step of our methodology, which is the subset. So as you can see, the image is pretty large, and we are only interested in a specific area. So we are going to reduce the extent of the image so that we reduce also the size of the image, and the processing time is improved. So for that, we go to raster subset. Okay. So there are different ways to subset the image in Snap. We can first of all do spatial subset, so reduce the extent as we are going to do, but we can also do a band subset to reduce the amount of spectral bands that are in our product, or we can even do a metadata subset. So, well, a lot of options. But today we are focusing on the spatial subset. And for that we have, again, 3 options. We can either draw the new area we want within this thumbnail. So it's very convenient sometimes if we don't want to be very precise. But if we want to be a little bit more precise, we can use pixel coordinates or geo coordinates, LAND01. So today I'm using pixel coordinates, but okay, you could use any other method. So let me put the numbers properly, very quickly. And okay. Okay, so this is the new extent that we want for our image, and once you are finished with that, we just need to press OK. And the new subset product will appear here. Again, check this number 3. So there is this order. And as you can see now, the subset, let's say, keyword is added to the product so that we can keep track. So let's have a look now to this subset. Again, right-click, open RGB, and then True Color. And we close, well, let's leave it together. So a very nice feature of Snap is that we can put 2 images together and compare them visually. And for that, it's very easy. We just need to go to Windows, Tile Horizontally. In that way, both views are combined, and we can see the difference of the subset versus the original. So you will see. Well, so if I move around, the image has to load here, but don't worry, it's okay. But you can see already the difference of size between the images. Of course, it makes sense. This is what we have done. So let's close the view number 2, and let's focus on view number 3, which is our subset product. So what's our next step for the crop mapping? So next, we want to do, or we want to create the training vectors. So remember I said we are doing a supervised classification. So as in any other supervised classification, we need training data. And to put the training data in the Sentinel2 product, we have 2 options. We can either create the polygons in Snap, or we can import the polygons from our own files. So I will show you very quickly how to do both things in case you are interested. So let's first of all zoom to an area. For example, I'm going to focus on the river. So definitely this is water, I know that, and I'm going to create a polygon to represent that. So the first thing is to expand our product number 3, the subset. And we go to the vector data. It's here where the polygons will be saved. So right now we don't have any. So the first thing to do is to create what in Snap it's called a new vector data container. And we give it a name, so you will see. Let's call this data container water. And this is, let's say, like a class. So we just press OK. And now this vector class or vector data container, as it is called, it's created. If we open it, you will see it's empty. There is no geometry here. So we need to add those polygons. And for that, we can use the drawing tools, either the rectangle or the polygon. So I'm using the polygon, and we just create our water polygon like this. And to finish the edition, we just double click. So now if we go to the water vector data container again, and we open it, we see that we have a polygon here. We have a polygon here with the coordinates of the points, etc. So we can keep doing that and create our training data for water. For example, we can create here another polygon, etc. Now, if we want to create another class, it's again the same process. So just go to vector, new vector data container, and then, for example, let's call this new class RUS. So we just press OK. And now, pay attention to that. When we create a new polygon, Snap is going to ask us, where do you want to save this polygon? So when you use the drawing tool to draw the new polygon, it will say, okay, is it a water polygon or a rice polygon? So it's a rice polygon now, and now we can just draw a polygon here, or we can draw a polygon here. Again, it's asking for the same, etc. So this is how in Snap you create training data, okay? But I'm not going to do that because I need a lot of training polygons for my classification, so I'm going to import them already. We have here our vector data with no training data, and we go to vector, import, Esri shapefile. Why? Because I have my polygons in this format. Okay, maybe you have them in CSV or whatever. So I'm selecting this option. Now I'm navigating to the path where I've saved my polygons, and I'm just selecting all of them, and I'm pressing open. So now when you're importing a polygon, Snap is asking you if they should be imported separately or not. So I'm saying no, because I want each polygon to be independent so that they can be treated separately. Okay, so it's asking that for each of the polygons. Okay, so here we have our polygons on top of the image. You can change the display of that by going to the layer manager in the right part, and as in other GIS software, you can activate or deactivate the view. For example, you can remove the study area or put it back again, etc. So once this happens, we are ready for our next step. So the next step is going to be Reproject. So we need to make sure that the polygons and the image have both the same metadata so that the classifier will not have any confusion. And for that, we'll go to raster, geometric operations, reprojection. So again, we face the same interface as before. We have the input-output tab. We have the source product. It's going to be number 3. And then we have here the output details. So just make sure that you are specifying the path where you really want to save the data. So for example, here. And then we go to the reprojection parameters. So in Snap, there are 3 options to define the new coordinate reference system. You see here you can use a specific EPSG code. You can select it in different ways, but I'm using a very convenient one, which is the automatic UTM zone. And it's very convenient because you just need to put that, and the software will automatically locate the image in the UTM grid and will say, okay, this belongs to the UTM, in this case 29 North. So that's all. Then click run and the reproject will start. Again, I'm not running this. I will directly show you the output. So I'll close here and I go to open my reproject product directly, which is this one. Okay. So here we have the product number 4, and now we can open it again with right click, open RGB, and OK. So now we can close this view again to avoid confusion. And here we have our reprojected image. We can remove those polygons from the view in the same way. So just for visualization, I will remove all of them. Yes. And don't worry, the image is coming. There it goes. So the original Sentinel-2 image was was projected in zone 30 North, if I'm not wrong. This one, because it's a subset, it's a little bit, it's located in a different way. It's 29, and that's why we see the image a little bit balanced. So this is our image. So now the next step before running the classification is going to be a mask. We want to really remove all the pixels that we do not want them to be part of the classification. And how you do that, it's very easy. It's like in other softwares, this is called a clip. Not exactly the same, but we are going to remove those pixels that we do not want. For that, we go to raster, mask, LAND01 mask. Here again, we define the input and output, and we go to the processing parameters. And we select the use vector as mask option. And we unclick the option use SRTM 3 seconds. Now the software is asking us which is the shapefile you want to use, which is the vector you want to use as a mask for the image. And since we have, there we go. You see, remember to make sure that you are selecting the appropriate input. So I'm going to select as mask the study area vector. I want to remove all the pixels that are outside the study area. So once you are ready with this, remember to do this, you can click run, and again the process will start. And again, I will show you directly the result. So let me open it again. This is the mask product, this one, open. And here product number 5, we can again go and open RGB, okay. So there it goes. This is the marked product. Let me again remove the vector data from the display. And now we see that the Sentinel image is completely cropped with the size of our study area. Maybe you didn't see that, but this is exactly the shape of our study area, which is this pink layer on top. And the remaining polygons, by the way, are the training polygons. So I will show you that. So the polygons I imported before are the ones that will be used for the training of the classifier. So you can see some of them here, for example, here, etc. I will talk more about training data later. So now we are ready. We have done all the pre-processing we need for our classification. And as I said at the beginning, we are running today a well-known and a very famous algorithm, which is the random forest algorithm. So let me, in case you don't know about this algorithm, let me give you a very basic introduction to it. I think it's very important, and I think it's very relevant as well, because it's used a lot by the remote sensing community. So it's maybe a good chance to learn a little bit more. So for that, I'm coming back to my presentation, and to explain the algorithm, I will use a very easy example that is not related to remote sensing, and you will see why. So let's imagine we have the following task. Let's imagine we want to classify the world population between boys and girls, okay? So as always, in all the classification tasks, we need some knowledge about our target. So we all know that we all have characteristics and attributes, right? So we have a height, a weight, an eye color, the hair, etc. So you can think about any other characteristic about people in general, okay? So knowing that, and as always in statistics, we cannot work with the complete population directly. We need some samples, and with those samples we can build a model, and with this model we can then derive conclusions about the population, and those conclusions can be more or less accurate. You can be more confident or not, but this is how it works. So we need some samples, and what we call more often in remote sensing, training data. So the training data is going to be you, the attendees to this webinar. So how is the random forest algorithm going to do the work to classify the world population using you as training data? So let's have a look. So here we have the training data. This is all of you. And the first thing that's going to happen is that we are going to select, and pay attention to that, we are going to select a random subset, okay? A random subset. So for example, this one, the red people. And then random forest is going to do the following thing. It's going to put it back. So this is called in literature with replacement. So we create this subset randomly, and we say, okay, this is subset number 1, and then we put it back to the training data. And then we are going to create another random subset, for example, the blue one. But since we are working with replacement, it might happen that some of you will be selected twice, or once, or will not be selected at all for the creation of the subsets. So for example here, we can see that some blue people are selected, but also some of the red people from before. 4. And then the process keeps going like that. So we put it back, and we create another subset and another subset, and like that. So just remember, the selection is completely random and with replacement, okay? So then, what's going to happen? Well, now we are going to create, for each of those subsets, we are going to create a model. And random forests use as models where it's known as decision trees. So decision trees are predictive models that split a data set into regions by using a set of binary rules to calculate a target value for classification. It can also be for regression, but today we're doing classification. Okay, so follow my example. It's very easy. We have to ask a question to the training data so that we can split the training data in boys and girls. Okay, remember, this is training data, so we know the class you have because you are training data. So again, random forest is going to pick, and this is very important as well, randomly a subset of characteristics of the training data. So you remember we all have hair, weight, height, etc. Well, we are going to pick randomly not all of the characteristics, but just a subset. And out of that subset of characteristics, we are going to select the one that is providing the best split for the data. I'm not going to cover how this is exactly done because that's too much of detail for the algorithm. If you want to know more, I will definitely recommend you to check literature. But this is how it's done. From the subset, we select the one that provides the best split between boys and girls, because this is our final classes. So, for example, is the hair short or long? Then another binary question about, we select again another random subset of characteristics. We take the one that in this case provides the best split, and we ask again a binary question. Is it higher or lower than 170 centimeters? And if so, well, you will be classified as a girl or as a boy. And if we go back to the other branch, again, we select another subset, and again, you will be asked a question, and based on that, you will be classified as girl or boy. So this is just an example, of course, but this is how the decision tree is built in a basic way. So remember, we are building this decision tree for the red subset. Now what will happen is that we will do the same for the other subsets, exactly the same. So for the blue and red subset, we create a tree, which is different from the other one. For this blue, green, and red, we again create another tree, which is completely different as well. And each of the trees has its own set of rules or binary rules that classify the people in this case. So what happens when you combine a lot of trees together? Well, you end up having a forest. So here's the deal, random forest. So now, how is this going to work? We have our model, and now the next step is to make some conclusions about the general people of the world. So let's imagine someone joins this webinar now, and we want to know if it's a boy or a girl. Well, these people will be sent, let's say, through each of the decision trees. And each of the decision trees, based on the questions they have, they will vote for a class. So each tree will say, this is a boy, this is another one will say, this is a boy, and another one will say, this is a girl, etc. So the class having more trees voting for will be the class that is assigned to this person. And this is how random forest works for classification. But now someone can ask, okay, what about accuracy? Well, I'm going to cover this very quickly, but what about accuracy in random forest? Well, you remember we were creating a subset, and then for this subset we were creating a tree. Well, random forest has a unique way of providing some accuracy assessment based, and this is important, based on the training data. So the people that are not used in this tree, because for this tree we are just using the red people, for these people which are training data, we know that they are girls or boys. So they will one by one be sent to the tree, and we will see if the tree votes for the same class as the one they have assigned. And in that way we can know if the classification is working or not. This is called in literature out of the bag. No need to remember that, just in case you want to check some papers and stuff, so that it rings a bell on you. So this is done for each of the trees, and putting together all this information, we can know the overall accuracy based on the training data. Pay attention to that. So now let's go back to the remote sensing world, and let's see how does that work for a Sentinel-2 image. So we have here our Sentinel-2 image. We have the blue, green, red channels, etc. And now, as you may know, well, the attributes of satellite image are the spectral bands. Those are the attributes in this case. And the training data is going to be some pixels that we have identified by overlaying a polygon on top of them. And for those pixels, we know the class, okay? This is how supervised classification works in general. So for example, purple pixels are, let's say, sugar beet, and green pixels are rice, and yellow pixels are wheat, etc. So the same process that I explained before is going to happen now. So for the training data, so that is for all the pixels, we are going to select a subset of them, and we are going to create a tree using the attributes to ask questions, to ask, let's say, binary rules. And we will create a lot of trees. So subset number one tree. Subset number 2, another tree, etc., etc. So now what will happen, well, let's imagine we have a pixel that is not on the training data. It's a pixel of our study area, and we want to classify this pixel. Well, it will go through each of the trees, and each of the trees will vote for a class. And again, the class having more votes will be the class assigned to that pixel. And if you do that for a complete image, you end up having a classified image using random forest. Okay, so this is an ideal case. So this is the theory of random forest. I hope you have understand the logic, because it's very important to know how the algorithm is working to understand the result we will get. So let's go back to SNAP, and let's go back to our exercise. Now we just need to do the random forest classification, and it's very easy. The software does everything for us. So we just need to select the product number 5, and we go to raster, classification, supervised classification, remember, and here we have the algorithm, random forest classifier. So we click here, and again we have this interface. So the first thing to do is to add the input for the classification. So to add the Sentinel-2 image that we are going to use. Remember, today we are only using one image. Of course, you can do multi-temporal analysis, and I will talk about that at the end. So how to add images here, you can click in this button and navigate to the path of the image, or you can just click here and all the images of SNAP will be opened. But since, well, now what we can do is also to update the metadata of the images. But remember, we are just working with the image that has been gone through all the pre-processing. So this is this image here, the one that is masked. The other ones are just pre-processing, and we don't want them. So we select them and we press minus. Okay, so this is our input image. Then we need to set a couple of parameters for random forest. And that's why I also like the random forest, because you just need to put 2 parameters and then that's all. And it's also very easy to understand how it works. So the first thing is to say, okay, we are doing a new classification. We are training on vectors because we have uploaded those polygons. We want random forest to evaluate the accuracy based on what I explained about the accuracy and how it's done in random forest. We can select now here the number of training samples, that is the number of pixels that will be used for the subsets, and the number of trees in the forest. You remember? So you can check on literature. 10 is a good number for testing, just to check how the training data is working. If you check literature, you will see that the more trees you have, the better. It's not an exponential function, but until certain level, this is true. And usually in literature, you see that 500 trees are enough to, well, reduce the noise and have a homogeneous response. So I'm going to put 500. The next step is to select the training vectors. Of course, all of them I have imported those polygons before, but be aware, do not select the study area because this is not a training vector. So we have here the polygons for sunflower, for rice, water, built up, etc. So those are the crops I'm going to classify. The next step is to select the characteristics of the Sentinel-2 image that I want to use in my classification. You remember those questions that we asked during the trees? Well, they are based on the attributes of the image, and here we can select which are the attributes that we want to use. So I'm using all of them. You can select, for example, RGB and near infrared only. You can do whatever you want, and you can even do different combinations and check how this affects the result. But be aware that the more information the classifier has, the better for him, until a certain level. Be aware of that as well. It's not exponential needed. Then, well, that's all. We just need to check that we are saving our product properly in the path that we want. Again, it's adding this RF keyword to the product name, and that's all. So we just press run and the process will start. It's very easy. Again, let's close this and let's open directly the output of this operation. And let's have a look to the crop mapping result. So I have it here, and there it goes. So the first thing you have to do when checking the output of Random Forest is to expand the product and go to the bands folder. As you can see now, we do not have the spectral bands of Sentinel-2 because this is not a Sentinel-2 image. We have the classification and the confidence. What is the confidence? Well, Snap implements Random Forest with a different version in which a confidence interval is derived to know which is the confidence that the classifier has for each pixel class. Okay, so I'm not going to go too deep into that. You can check that on literature. This is just for basic implementation of Random Forest. So, but what you have to know is that you have to check some parameters here. So if we go to the classification, I will show you that now. We go to properties, and we are going to remove the valid pixel expression. And why? Because if we leave it like that, only the pixels that are classified with a higher confidence than 0.5 in this case will be shown. And we do not want that. We want to show everything. For this example, of course, for other implementations of classification, you can have your own rules. So we put 0 and we close. And now let's just double click and have a look to the image. So there it goes. So first of all, let's analyze this little by little. First of all, let's remove the vector data that is on top. Okay, now let's change the color scheme. So you can have your own color scheme. You can change that manually here in the color manipulation tab, which is in the lower left corner. Or you can also import a specific color palette that has been created before, and that's very useful sometimes. So I have my own color palette here that I created before, so I will just use it. And now let's have a look to the image. So this is our classification using Random Forest, using only one image, and etc. So what can we see? Well, we see from this perspective rice fields in light green. We see also the water in blue. We see some rice fields that are still flooded. This is a common, well, that's how rice is grown. But now let's have a closer look. For example, here. So here we can see different colors, different crops. And we can see that some classes are classified pretty well. For example, sugar beet in purple looks very nice. The fields are identified pretty sharp. The boundaries of the fields are well defined, etc. For example, corn in yellow also looks very nice. Some other classes, such as tomato and cotton, have some confusion. But of course, this is something that you have to know, and that's why it's important to understand how the algorithm works. So how can we really interpret this result? Well, first of all, The results depends definitely and a lot on the quality of your training data. So the polygons we were importing. So a different strategy or approach to create the polygons will definitely change your result. More training data will help the classifier. So in case you're interested, I really recommend you to just give it a try. I mean, open a RUS virtual machine, set your own study area, location, and play with the training data and see how different strategies can improve or not, maybe, the classification. Remember, for example, here, talking about the classification, we see the boundaries of the RUS. They are very clear. We can even see some paths through the fields. Some of them are better detected than others. Okay. We see here again some confusion between some classes, for example, the red and the gray, etc. So also something important to mention is that random forest is a machine learning algorithm. And in an easy way, what does that mean? Well, it means that there is no, we are not assuming anything from the data before the classification, as in other parametric classifications. So what does that mean? It means that the more information we give to the algorithm, the better it will learn the relation between what you have, your image, and what you want to have, which are your classes. So because of that, if we add a multi-temporal approach, if we add more images, if we add more training data, the classifier will have more inputs and will be able to learn more this process. So I really, if you want to give it a try, I really recommend you to have a look and check, for example, a multi-temporal classification. Maybe, for example, adding vegetation indices. Maybe if we add NDVI, this can help to differentiate between a crop and another. Maybe not. Sometimes vegetation indices can help or not. Well, you can test that. And also something that I want to mention about the random forest and SNAP. Well, random forest provides an accuracy assessment, as I said before, using what it's called out-of-the-bag samples. But remember that this is just a validation on how good the classifier was able to fit the training data. So if this is not, let's say, a complete assessment of the accuracy of the classification, it's just an assessment of how good the classifier was on classifying the training data. So if you want to have an accuracy assessment of the classification, you need an independent validation data set, and you can do a regular accuracy assessment such as a confusion matrix, or you can derive some statistics such as the kappa coefficient, etc. Unfortunately, this type of accuracy assessment is not supported in SNAP, so personally I would recommend you to try in QGIS. They have very nice tools for that. So this is how you perform a crop mapping analysis on SNAP in a basic strategy, let's say. Something important from an operational point of view is that you can export this result. So let's imagine you want to send this image to another software or whatever. Well, you just need to go to File, Export. Sorry, you first select the image and then File, Export, GeoTIFF in this case. I'm using GeoTIFF. You can use another format. So we click here, and that's all. We just need to put the name and save the image wherever you want. And in that way, you can export your results. And of course, for example, you could download that from the virtual machine to your local computer and do other analysis, such as area per crop or change detection maybe from one year to another, etc. So that is all for the crop mapping analysis. That is all for the interpretation of the result and how it can be analyzed and improved, etc. Let me give you, before finishing, some take-home messages, especially about RUS, and to let you know how these kind of applications are better implemented into the RUS environment. So for that, I'm going back to my presentation. So remember that nowadays we have a massive volume of data produced by the Sentinel satellites. There are more Sentinel satellites to come. It will be huge, the amount of data we have. And that's great because with more data and new algorithms such as the random forest and machine learning options and much better implementations, we can derive and we can produce results that can help a lot. For example, in crop mapping, in agriculture, monitoring, etc. So with the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all this information. Let's imagine, for example, we want to do this crop mapping exercise, but instead of using one image, we want to use 20 images because Sentinel2 has this great revision time and we end up having a lot of images. Well, it might be that in your computer, even though it can be very powerful, it's not possible because it will at some point crash. So we have this challenge now, but we also have solutions. Of course, in addition to that, it's also necessary to explain how the data can be used, and I mean, from the Sentinel community, we have to produce some. You have to explain to people how to use the data. For example, how to do crop mapping with Sentinel2, what you have to take into account and what not. So we have those two challenges to solve. And RUS is exactly here to solve that. So the RUS service provides those free cloud computing environment, those virtual machines that you have seen me using in this exercise, and they are ready to use. So you can have the data ready to use, you have the software ready to use, the storage, which goes up to 1 terabyte or even more if you need it, or it goes up in processing capacity also for multiple cores, etc. So it is a great tool to process and handle the large amount of data we have now. And in addition to that, we also have a dedicated help desk with Earth observation experts to support your activity. So let's imagine you want to repeat this exercise, crop mapping, in your local area. You want to give it a try. You want to see how well you can identify your crops in your region. And you have some doubts, or you don't understand some steps, or whatever. Or maybe in another application, such as burn area mapping or whatever. Well, you can contact us, and we will a team of Earth observation experts will be there to reply to your doubts and help you in your process. So before moving to the Q&A session, let me tell you again how you can repeat this webinar. Let me remember as well that this webinar is being recorded and will be published, but you can also repeat the methodology I've done. And how to do that is very easy. Just go to RUS-Copernicus, register in RUS, and open a new user support request. And within the application procedure, you have to specify the training code. So the training code for this webinar is LAND01. So you can use it. It's ready to use. You can send your applications. We will give you the virtual machines as the one I've used today with the Sentinel2 image, the training data, the software, and everything. And then you can check different implementations. You can also load your own Sentinel2 images and perform your analysis in your own area. So it's free for that. So that's all from my side. Thank you very much for your attention. I really hope you have learned something today. Remember, this is the training code. Here we have the two websites of RUS. And of course, we are in social media, so you can follow us on Twitter, YouTube, Facebook, and LinkedIn. It's RUS Copernicus. You will find us. So thank you very much for your attending this webinar. Thank you also to my colleagues that were involved. And well, it was a pleasure for me to be here, and I hope I will see you in the next webinar. Ciao.